Hello. Today we are going to talk about Tagless Final. In particular, I will focus on the part that most tutorials are missing, the part about algebras, the part about what actually makes an algebra. But before we do that, I want to introduce the general concept first. So, Tagless Final is a way of embedding domain-specific languages in a host language. In our case, our host language is going to be Scala. The basic example that most tutorials give is the expression algebra. In our case, it's going to have three operations on objects of type A. One of them is going to add objects of type A, two of them in particular. One of them is going to provide a zero object of type A, and the other one, the last one, will provide an object corresponding to the value of 1. So, given this definition of an algebra, we can write a program. So we can write a program that will work for any expression algebra. And I'm going to write a program that adds the number 1 to the number 1 to the number 0. I am importing all the members of the expression value, but you don't have to do this. This is just to make the code more concise. So we're going to add, then add, and I'm going to add 0, 1, and 1. So let's run this, but wait, we can't run this yet. We don't have an expression of A. So we are going to write an interpreter of the expression algebra to the type of int. So our implementation is going to provide all these methods, all these operations for integers. So add will simply use the plus operator to add two integers. 0 will be the number 0, and 1 will be the literal number 1. So now I can call our program with the interpreter of our algebra. Let's see what this gives us. So we get the number 2, which really makes sense if you think about it. We just add a 0 and two ones, so we get a 2. So that's most of the concept of Tagless Final. But we are missing one really important thing about it. This algebra doesn't have any laws. There are really no rules as to what the implementation can or cannot do. We could implement this for I/O or any other effect type or any other monad, anything like that. And there are no rules as to what the implementation should do. But given these three operations, we could define some laws that might seem sensible to us. For example, we could have one law that, if we have a symbol for this add operation, we could say that 0 plus 1 is 1, 0 plus anything is anything, so we don't really need the first law. This should be true, right? Also, anything plus 0 is this anything. And this already gives us some rules as to what the implementation should do. We don't really have any laws about 1, but 1 is one of the ways of getting a number different than 0, and then we can add them. So this anything could be 1 or 1 plus 1 or 1 plus 1 plus 1, and so on. So we could have these two laws and maybe add some other operations so that we could define more laws. But only then this would be a real Tagless Final algebra. Otherwise, it's just an interface that's polymorphic. We can extend this idea to work with effects so that we could have an effect here, and maybe our objects would be A's, but we would have an f of A in the result. But let's not get carried away. So let's add a new algebra. This time it's going to be a much more powerful algebra that will not just add numbers and create new numbers, but this one will actually allow us to store some values. We are going to define a KVStore algebra. It's going to be parameterized with the effect type, as well as the type of the keys in our KVStore and the values. I decided to abstract out the effect type because I am going to have implementations for more than one effect. And also, the effect that my algebra is going to use is not relevant for its implementation. So I don't need to include the information about the effect in my algebra. So let's define a couple operations. First of all, if we want to do anything with a KVStore, we need to write values. So I'm going to add a method for writing. And that's going to take a key and a value and return f of unit. So this will just run an effect, but not yield any useful value, just unit. I'm going to add another method, another operation that will get a value at a given key and return it in an option in the effect. It has to be an option because I don't want to deal with exceptions. Otherwise, I would need a bifunctor type or something like that to make it explicit that this method may not return a value. If we haven't written one, then we will not get one. And I also want the option to remove a key that's already been written. So we'll have a method called delete that takes a key and returns f of unit. And this is going to work even on keys that haven't been written yet. But all these rules that I just mentioned, they need to be defined somewhere. So this is why we will have laws for this algebra. And here is what actually makes an algebra an algebra. We have a set of objects that we are working on, and these are the keys and the values. Because these are part of the algebra, we have keys in the parameters of the operations, as well as in the results. We also have unit, which is a very specific value, and option, which is an effect that may not contain a value. Additionally, to our objects, we will have operations on these objects. Write, get, and delete. And we are also going to have laws, algebraic laws that define how these operations interact with each other, these operations on these objects. So let's look at the laws that I created for us. So given a KVStore of key and v, we're going to have a couple very useful laws. First of all, if we write a value at a given key and we try to get it, then this should be the same as writing that value and then lifting a pure value in sum, so that it's an option, and then lifting that into the effect. We will also have another law that if we write and then we get twice, then that should be the same as getting once. So this basically means that these two gets return the same value. So now it's important to notice that I didn't just do k sum pure, because this doesn't really make sense. The values that we are going to get out of these two sides of the equation are going to be the same, the ones in the effect. But the effect is actually going to behave in a different way. And it'll be easier to see on the first law. I have this sequence write and get. And if I only did this, write and get is the same as pure, then I could take this part and get the equivalent expression and replace the occurrences of this first one, this first left side, here. So let's look at this new version of the second law. We have a pure value lifted to f, then we get, and that should be the same as the pure value lifted in f. And because a pure value lifted and then ignored because of the right shark operator is the same as just not doing that, we can simplify our expressions. So you can clearly see that this doesn't make sense. We cannot get a value and expect it to always be there because we didn't write it in the first place. So this is why we cannot just write laws like this. We must also verify that the effect has happened. So let's roll back to the correct version. So now we are back. We are writing and getting, then writing and lifting a pure value. Because get doesn't actually change any state outside our application, we can do that. But if get also had effects that would modify some state, we would also have to repeat it here. So the first law is that basically whatever we write, we can get later. And if we get twice, that's the second law. If we get twice, that still yields the same value as getting once. We'll have another law that if we write twice to the same key but with different values, then if we will get the second value. And we are not really saying here that this is v, the second value, pure of f, because we don't need to. This is guaranteed by the law of get being equivalent to pure. The part that really matters, you can really see that this expression has been duplicated in here. So we don't really need to verify that. This, we could just substitute it with the other version. But let's get back to the one we defined previously. We'll have another law that if we delete, now this is new because we didn't have any laws for delete before. If we write and then delete and try to get the value, it's no longer going to be there. Also, if we write, then delete, we can still write again to this key. And that's going to be equivalent to just writing the second value and then getting the value at that key. Also, we have some laws about independence. So laws that specify what happens when we have multiple keys in our key value store. This is really important to test. So we come up with one key and one value and then another key and another value. We verify that the keys are not the same, because if they were, that would be a different law. That would actually be the latest overwrite wins law. But then we would have a completely different code path. So I'm making this assumption here. If this is true, only then we are going to test this law. Only if these two values are different. So we write the two values at the two keys, and then we get them both. On the other side of the equation, we will write these two values and then lift them in the effect. And these parts have to be the same. We will also have a law for delete independence as well. So if we write two values and delete the first one, then we can still get the second one. And also if we write two values to two keys, and then delete the second key and get the first one, it will have a value. We could, but we don't need to test what happens to the other value, the one that we deleted, because that's guaranteed by other laws. So this part about conditional laws, it's still present in these two. So we have three laws that verify that the keys are not the same. This is something that I came up with just for this example. So it's nothing standard, but it might be useful to you. So these are our laws. Now what do we do with the laws? We have to test them. But what do we test if we don't have an implementation for a key value store? So let's look at the implementations that we have. I'm going to have two implementations. The first one is going to be based on the monad state instance. we are going to have a monad state instance that contains a map of keys and values. This is the simplest representation of an in-memory store, just a map. And because this is going to be purely functional, we will not just modify a var in memory. We are going to interact with our state in a functional fashion using the monad state abstraction from CATS MTL. So this is going to work for any effect that can provide a monad state instance. with a map inside it. And this is just a KVStore of F, key, and V. Our write operation will be just adding to the value to the map. Our get operation will be just getting from the map, and our delete operation will be just removing the key from the map. I'm also going to have a second implementation based on Redis. And I'm using Redis for CATS here. So we are going to require two algebras provided by Redis for CATS. One of them is going to be string commands, and the other one key commands. We are going to use this for deleting the keys. So in our write implementation, we will set the value on the given key to the given value. In our get operation, we are going to call get from the string commands. And in our delete, we are going to call the del method, the del operation in the key commands algebra. So given these implementations, let's see if they actually pass our laws. I had to define a trait called KVStore tests that defines how the laws are going to be run. So this is a pretty standard thing based on the CATS and Discipline setup. I encourage you to check this out. I will post some links in the description. But basically what I'm doing here is saying how to run all these laws. So all these laws are enumerated here, and we are using Scalacheck to run them. But to run a law with Scalacheck, we are going to need a few implicit instances. We are going to need an arbitrary instance of our key and our value. Arbitrary is going to be the thing that supplies values of these types into our tests. So we are not going to write these values ourselves. We will not have to come up with examples. The framework will take care of that for us. We will also need a way to compare the results of all these gets and so on, because if we look at the laws, for example, the persistence law, the result of it, the type of this is equal f of option not v. And to actually verify this equivalence, we need an instance of eq of f of option of v. And because I have one place where I compare a tuple of options, I also need this, an eq of f of a tuple of options of v. And also there's an option outside because this law might not be run in case the keys are the same, if you remember that. So I define a rule set. I'm using the default rule set, so I just give it a name. There is no parent because the KVStore algebra does not have a parent algebra. And then I enumerate all the laws with some names. Given that there's a handy helper, KVStore tests apply, that I'm using to basically create these tests. So once I have an implementation, and I do, let's look at the state implementation first. I'm using the state monad here because it has a monad state instance that's very easy to use. I imported it from CATS MTL in the import list. And now all I need is to basically run this to use these laws. This is the rule set that I had. And I'm calling check all so that the rule set is executed. I also need a couple of things like equality, but let's look at that in a second. So this is the KVStore test, but I also have the test for the Redis implementation. It's in a separate class because I am supplying a custom configuration for Scalacheck here, one that ensures that the tests are run sequentially. I'm also using a client This client value comes from the Redis suite trait that I defined below. I'm defining a way to generate an arbitrary string because that will be my key and value. And I don't want empty strings and I don't want weird characters in my strings. So I'm just using a non-empty string containing alpha characters. So pretty much just A, B, C, D, and so on. Now we can define our key value store instance using the Redis client, which is used here through the implicit Redis commands instance, which is also a super type of all these string commands and key commands algebras. So now I can run check all again. I give it a different name here, and I supply the rule set again. So let's run that. First, I'll need a Redis instance. So I'm going to run one in Docker Compose. This will just start a Redis instance on my local machine on the default port. And in another window, let's run the tests. As you can see, the tests for the in-memory instance passed very quickly, but the Redis instance takes longer to run. This is because I cleared the database before every action. So the test passed. Let's look at how this all works underneath. So I mentioned that I needed some extra utilities here to work with the state monad. So let's look at that. First of all, I needed a way to compare two programs of type state. As you can remember, we were requiring an implicit eq of f of a, and this is where it comes from. This is how we compare state programs. And because we should not really depend on the actual state, but on the interactions between operations, I am deliberately not testing what the state is after our action. I am only checking what the output is. So I am not requiring an eq instance for the state, but just for the output. And my implementation of equality for state is only based on the output of it. So I check that for every input state that I can come up with, if I compare the result of the first action with the result of the second action, they have to be the same. And if that's true for enough instances, as defined by check, which will also use the arbitrary instance underneath, this has to be successful, right? If the equality is not matched, then this check method will throw an exception and try.isSuccess will no longer be true. So I'll have a failed test. I also define a couple other useful things, like the context shift instance that we're going to need for Redis, and a logger, which we're also going to need for Redis, as well as the state instance, which is now just made implicit. So that's it for the state implementation. But I also needed to do some things to get Redis to work. So this is the Redis suite trait that I mentioned before, which will provide some utilities for Redis. First of all, I have a resource that defines how to connect to a Redis instance. This is pretty basic stuff from Redis for cats. If you want to learn more about how to use this, then I encourage you to look at the documentation for Redis for cats. But we're not going to focus on that here. I start the client using the resource.allocated method and unsafe run sync. Sadly, I have to do this because of Scala test. And I keep the shutdown hook. And now the most important part of this is how do we compare two programs in I/O? And I/O can run arbitrary operations, any kind of operation on the whole world. So how do we test what happened in there? And the answer is we don't. We only test what the output is, but we also make sure that every test, every equation, every side of an equation starts with a new fresh state in Redis. So we are not going to inspect that state directly, but we're going to make sure that it's clean before we run the test. So that's what happens. We compare the I/O values by what happens when we run them having cleared all the keys in Redis first. And then we just make sure that in case of any exceptions, we also compare that. And I use unsafe range sync because that's what eq expects. It expects a value that can be compared to another value of the same type. And in the after all method for Scala test, we removed all the keys again to have a clean database, and we shut down the client. And that's all. So let's add one more test. Let's get back to the laws. And while making this video, I realized I'm missing one very important law. And this law is that I can delete a key that's not present. So if I delete a value at a key, and then I get it, I'll get none of v in the effect of f. That's basically it. There's another law I could define. There's a law that I can delete a key twice. So if I have a key and the value, I can write to that key, then delete it, and then delete it again, and try to get it, and that should give me the same result as none of v pure f. In fact, I have to write the key with a value. So given these two new laws, let's give them some descriptions, and let's add tests for them. And let's run that. So the tests passed again, which means our implementations were lawful. So this is what makes Tagless Final algebras real algebras. We have laws for them and we test them. So I hope you learned something new today and that you liked this video. So please subscribe to my channel, like this video, and maybe use the bell icon so that you get notified with every new video. So thanks for watching, and I wish you a happy new year.